my time working with national statistical offices around the globe. Good to see you this morning.
Hi everyone, this is Maher from the Public Authority for Civil Information in Kuwait. Nice meeting you all.
Thank you everyone. Before we get started, I do want to share a few housekeeping items with you all on the line. I do want to let you know that the webinar is being recorded and we will send you an email afterwards pointing you to that recording so you can go ahead and view it again or share it with your colleagues. There will also be an opportunity for you to share your questions. We encourage you to share your questions via the questions panel within your webinar, GoToWebinar panel. Go ahead and type in your questions and we'll go ahead and take those where we seem appropriate, but we'll most likely save most of them towards the end. I also want to give you a heads up that we will be conducting some polls just to help keep the webinar engaging. So we look forward to hearing from you then. So that with that, I'll go ahead and take it away by passing it over to Omar so he can go ahead and kick us off. So Omar, do you want to go ahead and take us over?
Sure. Thanks, brother. So I want to start with the agenda. I promise you it's going to be a very exciting webinar today. We have a special guest, as Mallory mentioned, Maher, joining us from PASI, a leading organization that has used deep learning with Arcgis. Maher is going to present an amazing use case for the work today. I'm very excited to have him, so thanks, Maher, for joining. And this is pretty much our agenda today. We're going to start by an intro to AI and AI in Arcgis and why GeoAI for national mapping and statistics. We're going to have some focus on the imagery deep learning capabilities as we think this is so valuable for our national mapping and statistics customers. We're going to show an end-to-end demo in Pro first for detecting building footprints using deep learning. We're going to have the PASI use case. Maher is going to present that amazing work. Very much looking forward to it. We're going to have another demo for using the deep learning tools for land cover mapping, high resolution land cover mapping. We're going to show you a glimpse of the other use cases we're doing with other customers, and we're going to finish up with some resources and Q&A. So with that said, I want to start with demystifying AI. It's a buzzword that everyone is hearing right now: machine learning, AI, neural networks, you name it. And it really boils down to three main things: artificial intelligence, machine learning, and deep learning. So artificial intelligence, think of it as the big idea of achieving human-level intelligence. And it's not a new idea. It's been there since the 50s or even later. Machine learning is a field of AI that's about learning from data to derive rules and extract patterns instead of being explicitly programmed. And deep learning is one specific machine learning technique. It's using deep neural networks, and it's becoming very good with high-dimensional data like images, voice, and text. So we're going to see some applications for object detection and feature extraction, for example. And one thing to mention at the beginning is AI is not a product in Arcgis. It's a capability that's spanning a lot of products. You can see it today in the Arcgis API for Python, for example, Arcgis Notebooks, and a lot of other products. If you look at the machine learning capabilities in Arcgis today, it's spanning four main capabilities: classification for imagery, making prediction for geospatial events, making clustering with vector data, finding patterns, and recently deep learning capabilities with imagery that we're going to focus big time on today. There are three main patterns for this AI, machine learning, deep learning world intersecting with the GIS world. We call it GeoAI. And the three main patterns are: first, object detection and feature extraction from different kinds of imagery or videos. Think of drone feed, satellite imagery, you name it, and bringing this to the GIS to do spatial analysis. So we're going to show a lot of examples for this today. The other category is making predictions, right? So predicting geospatial events, and then finding patterns in geospatial data. These are the three main patterns that we see with GeoAI. And with that said, I want to pass it over to my colleague, Mark, to help us understand why GeoAI for national mapping and statistics. On to you, Mark.
With national mapping and statistical organizations, they're using artificial intelligence combined with geography to enable us to do a number of things, including predictive analysis, feature and object detection, particularly, visualizing patterns through spatial analysis, for example, clustering of objects to see where concentrations are, classification of things like land cover, and anomaly detection to find needles in a haystack. national mapping and statistical organizations are facing many challenges. These are including things like expanding stakeholder and user expectations from governments and industry, national government organizations to individual citizens. They're seeing escalating demand for a broader range of information products, from maps and data to web services and analytics. They are needing to do faster delivery of real-time information, coming from a large variety of sensors, all the way from delivery to delivery to many types of devices and apps. We're seeing increased demand for better resolution and higher quality data, and growing concern for information privacy. Many national mapping and statistical organizations have had their budgets cut and incomes cut by 25 to 50% in the last few years. This has resulted in fewer staff and overall resources to do the increasing work demanded of them. We're seeing shrinking timelines from initial point of data collection, from sensors to the daily delivery of information, all of which is required to meet the increasing expectations of these organizations. And as they wrestle with how to adapt to these changes, there's often a reduced perception of their relevance in parts of government and society. GeoAI is one solution national mapping and statistical organizations are turning to, enabling us to do more with less. This is increasing our responsiveness by speeding timely information to decision makers. It's increasing our relevance by leveraging technology and expanding our ability to increase data analysis and information delivery. This can be done by taking advantage of faster computing with more CPUs, parallel processing, and intelligent neural networks. It's enabling analysis by new GeoAI deep learning algorithms, tools, and location data. And it's enabling us to save time, money, labor, and even minimizing our impact on the environment by reducing fuel costs and emissions and their effect on the climate. We're increasing, sorry, go back one, Omar. We're increasing efficiency and expanding capacity by automating routine tasks to enable geospatial professionals to focus on higher value projects and outcomes, and empowering them to deliver much more information. And last, we're improving the accuracy and expanding engagement with our user communities. Next, Omar. National mapping and statistical organizations have identified their highest value workflows and use cases. We see them prioritizing workflows like change detection of areas to know where to focus their limited resources, and then change detection for individual features as they update their data. This is used to target feature identification and extraction of that data, to automate the collection of new and changed features, and reflect them in their systems of record. It also is looking at analysis and assessment, enabling them to streamline their analysis to add value and insights from the data they collect. Priorities with high value to national mapping and statistical organizations include change detection for new or changed roads, buildings, and land cover. We see feature extraction of transportation objects for national mapping and for census enumeration, and identifying things like commercial and residential buildings for national census pre-enumeration and high-resolution national mapping. And finally, we're seeing them use analysis like NDVI to identify changes in land cover for national mapping and agricultural census. So now I'd like to turn it over to my colleague, Omar Maher. Omar?
Thanks, Mark. That was a great intro to setting the context for our customers in national mapping and statistics. And I want to start by saying that the applications are endless, right? So we're going to show some applications today, but generally speaking, I want you guys to think from a deep learning perspective. Anything that a human being can detect under 1 or 2 seconds from an image or a video centroids, building footprints, land cover, trees, counting objects, street segments, you name it. Anything that a human can do under 1 or 2 seconds, you can generally automate this through AI. If you have good amount of quality training data, which is what we're going to show today, you can train deep learning models to make these detections, and hence saving time and cost and automating tasks, as Mark was mentioning. So with that said, I want to do some deep dive into the deep learning capabilities because we think there is a lot of need for these tools in the national mapping and statistics context. So let me start by having a quick highlight of the main capabilities when it comes to deep learning in ArcGIS. If you want to train a deep learning model to detect a building footprint or count trees or detect road segments, you generally need to do 3 main things. The first thing is data preparation. You need to prepare your imagery. So these are the reference functions for managing and hosting imagery using image server. But then you need to label data. And by label data, we need examples of what you want to detect. Generally speaking, deep learning models need examples for things. So if you want to detect building footprints, you need to give them a lot of examples for existing building footprints. If you want to detect road segments, you need to give them a lot of examples for image chips with classified pixels for what is road and what is not. With these examples, the models are learning, and we're going to see in action how this learning happens. So that's the first piece, like data preparation, labeling data. We have labeling tools, right? And then exporting this data into a format that is consumable by deep learning. Next comes the second part, which is training. You need to train a model. And there is no one type of model. There are different types of models, as we're going to see. And we're going to show you what kind of models to use in which context. But the bottom line is there are 4 different types of models, and we support all the 4 in ArcGIS today, natively. The third piece is inferencing, which is the process of using the trained model. Inferencing is using the trained model to detect the objects or classify pixels or classify objects. And we have these capabilities in ArcGIS today. So whenever you have a project that you want to use deep learning for, think of these 3 steps. And I want to show you now what tools we have for all the 3. Maybe you have one step back and talk about why deep learning in the first place. The answer is deep learning is achieving amazing performance results when it comes to computer vision tasks. So what you're seeing here are the results of ImageNet Visual Recognition Challenge. So ImageNet is a very famous competition that used to happen for computer vision tasks. So people would submit algorithms to detect different types of objects and features, right? And as you can see here, the average human rate in general with computer vision tasks is almost 5%. In 2017, the error rate of ImageNet was almost 2.3%, right? And I believe it's way, way less right now. So that's why we prefer to use deep learning for computer vision techniques versus the traditional segmentation or the traditional machine learning techniques. So the applications of deep learning to GIS are 4 main applications. There are 4 different, let's say, big types of these deep learning models for computer vision. The first is called pixel classification. So we are classifying each pixel, whether what kind of class this pixel would belong to. The application space in GIS could be something like improved surface classification, right? So there is a specific type of neural networks that we're going to use for this, like a UNet classifier. The second type is object detection. So you are detecting objects, right? And you are defining the location of these objects, like by a bounding box, for example. So let's say you are trying to count coconut trees, right? So we can use pretty much other kinds of networks like single shot detector for that. And then we have instance segmentation. Instance segmentation is segmenting each object. So it's not just detecting the object, it's drawing the boundaries around this object. And we can use math RCNN, for example, for that task. And finally, we have image classification. So you are classifying a specific image. Let's say you have detected a building footprint already, and now you want to define whether it's commercial or residential. Now, this is a yes or no question, right? Or multi-class classification, like this is commercial, this is residential, and we have different classification algorithms as well. So, first, before using a deep learning model, think of the type of problem that you're trying to solve, which is going to help you understand the kind of neural network you want to do. So, let's see the kind of the deep learning workflow in ArcGIS. In summary, it could be summarized by 4 main things. First is labeling training samples. So you need to produce some label data. And guess what? Most of you have existing label data already in your database because you're using ArcGIS as a system of record, right? So So we can use the kind of data that you have, or you can label new data. The second is preparing data for training, which is the process of exporting data into these image chips. The third is training a deep learning model, and you can train this model in Pro or using Python in notebooks, for example. And last, inference, detecting the object or classifying the pixel. So let's have a quick overview of all of these tools. So the first one, if you want to label data, we have a new tool called Label Objects for Deep Learning. We're going to show this today. We're going to find it under Image Classification on the Imagery tab in Pro, and it comes in Pro 2.5, where you can add new classes like cars, buildings, whatever class you want, and then you can start choosing how you want to label this by either having a polygon or a circle or a bounding box, you name it. Second is export training data for deep learning. I think a lot of you have seen this tool already. It's in there in older versions of Pro, and it helps you take the label data and export it to a format that's useful by deep learning models. Based on the kind of neural network that they're going to use, based on the kind of task, whether it's instant segmentation or object detection or feature classification, you're going to need to choose the specific type of the exported format. So for example, if you want to do pixel classification, let's say for finding building footprints, you're going to need to export in a classified file format. If you want to do object classification, like classifying whether this building is residential or commercial, you're going to need to export in label size format, and the list goes on. Third is training models. You can train deep learning models today in Arcgis Pro without writing a single line of code. This is a new GP tool called Train Deep Learning Model, where we're going to pass some parameters like the input raster and the model EMD file. We're going to extend this right now, and you can train models for different tasks in Pro today. You have another option, which is Arcgis Learn. It's a new capability in the Arcgis API for Python that would help you train models easily in a couple of lines of code, like 3 to 5 lines of code, easily building on top of fast AI PyTorch. And then you want to use your models, right? So we have 3 main GP tools for using deep learning models. You can use them in Pro, again, or you can use them in server or notebooks using Arcgis Learn. And if you want to scale your work, you're going to need to leverage enterprise and image server, right? And in that case, you can package your model as a deep learning package and upload it to Portal so that you can use it with multiple image servers, for example. So if you look at the high-level view of the workflow, you can see something like that. You have the imagery management capabilities to process and manage your imagery using the functions that comes with image analyst or image server. And then you can label your data using the label objects tool. You can grab your data, export it using the export training data for deep learning. You can train your model using the GP tools in Pro or Arcgis Learn. You're going to run the inference. And most importantly, you're going to do something with these detected objects or classified pixels. You're going to do some analysis, right? So using the space-time cube, for example, or field mobility app, you name it. The value of Arcgis is that bringing all of these pieces together in an end-to-end workflow. So why don't we see a quick demo in action? Before that, I want to do a quick highlight of Arcgis Notebook. So Jupyter Notebooks is a very good vehicle to do data science and machine learning. We have brought this inside Arcgis, and it's natively integrating with the different Arcgis pieces like the data stores and the analytics engine. You have this in Pro today, in Pro 2.5, and you have it in server. So with that said, I want to move forward to show you a quick demo of using these tools. So in this scenario, we're going to do 2 things. We're going to have a workflow to automate the process of building footprint detection across a big area, and then on top of this, we're going to classify these buildings. Think of it as this. You want to, instead of manually coming up with ways to find out your building footprint, you want to automate this, and you want to automate the process of finding their type as well. So let's start seeing, this is the area of interest. It's a pretty large area, as you can see, right? Where we have a lot of buildings. So if you look here, we have different kinds of buildings, and we want a way to quickly define or detect their boundaries. So we're going to need to label some data. So if you select your imagery and go to the classification tools, you're going to find label objects for deep learning. So if you click on that one, you're going to be able to add new classes. Let's add a new class here and call it buildings, for example. now you can label some objects, right? So if we go here, for example, this is a building, I can start labeling it, and by labeling it, I need to label it exactly as the output I want to produce. So I'm going to need to label the exact footprint, right? So that's what I'm doing here. So let's say I'm done with that labeling. In fact, actually, I've labeled already some data. So I've labeled all of these buildings, as you can see here. And now I want to export these into image strips that are usable by deep learning. So what I'm going to do is I'm going to go to analysis and look for a tool called export training data for deep learning. And this is going to take two inputs. Thereafter, that I'm using the imagery in that case. I'm going to specify an output folder, and I'm going to pass a feature class that I've just labeled. So building multi is the layer that has labeled all of these buildings. And I am going to choose a couple of things, like for example, the tile size, the size of the image chip, the stripe size, and I'm going to choose the format of the labels, right? So in that case, I'm interested to classify the pixels, right? So I'm going to choose classified type, and I'm going to run the tool. Once I run the tool, that's going to be the output. So if you go to the footprint training data, we're going to find two folders, images and labels. Images contain the exported chips, as you can see. Labels contain data about each pixel in these chips. Now I can use these to train a model. So if we go here, and if we look for a tool called Train Deep Learning Model, we're going to able to pass the footprint training data. We're going to point it to that folder. We're going to assign a folder for the output model. Let's choose any folder, like footprints model, for example, right? And then automatically it's going to see that it's a unit pixel classification, because based on the kind of label data, it understands that we want to do pixel classification using a unit, so it adjusts that. So I concur that I'm going to choose a unit, and I'm going to run it. Once I run it, it's going to pass over the selected imagery and detect the building footprint. Now, if you think about it, the detected building footprints are not going to be that smooth at the beginning, right? You're going to have something like this. So if you look at these are good, like these are some maps, but they are not that great, right? If you think about it, it's not that regular, for example. So one thing you can do is to leverage the post-processing GP tools that we have. So we apply some workflow here, and we're going to share a notebook with you where you can see a lot of details about that, where we're doing different things like using the majority filter and wrap up the polygons and then regularizing building footprints. And you can find details about that in the notebook we're going to share. And finally, when we run this, that's going to be, regularized building footprints like this. So you can see how beautiful these footprints are. They're very clean, and the boundaries are great. And we can see some examples here. Bookmarks. Oops. Sorry. So let's see this example here. So you can see how beautiful this building is classified. That's the kind of output that you get when you apply the post-processing. And that's why we think you doing this in Arcgis is great, because it's not just doing the deep learning, it's doing different functions that you usually need as well, right? Now, what about classifying the types of these buildings? Let's do that as well. To do this, you're going to need like similar training data, but that time you're going to need to have an attribute defining the type of the building, which what we have done exactly, right? So we have labeled each building, whether it's damaged or not, by adding an attribute to the attribute table and giving it a value, whether it's labeled or not. And if we go, actually, so that's an example here. I'm giving it the type whether it's damaged or not. In that case, I'm interested to find damaged versus non-damaged building. Right? So that's what I'm finding here. This is the training data I'm going to use. So the same thing, I'm going to go and use the export training data for deep learning to export these. So go to geoprocessing, export training data for deep learning, training data that just generated, right? And then once I run this model, this is going to be the result. So it has specified each building in this extent, whether it's damaged or not. Very similar in your case, you can do it commercial and residential. And you can see that you can automate this result across a really big area. As you can see, that's find all of these buildings here. And the more powerful the GPUs you're using, the faster you can do this. So with that said, I want to show you a real-life example and a case study that one of our major customers has done, Happy. And I want to pass it over to Linda to give us intro about this. Before that, Mallory, do we have a poll question, or do we have this after the Happy use case?
Yes, we do have a poll question. So let's go ahead. Now that you've seen a little bit through the demos Omar has conducted, let's go ahead and find out from you guys how many have actually used AI or would like to. So I'll give you guys a minute to go ahead and answer. Alright, I'll just give you a few more seconds and then we'll go ahead and share the results. And thank you everyone for responding. Alright, I'm going to go ahead and close. Let me go ahead and share the results. So it looks like a lot of you are interested or just are not sure how to get started. And thank you, by the way, for submitting your questions. We'll definitely address those great questions coming through. So with that, I'm going to go ahead and stop the poll and toss it over to you, Linda.
Thanks, Mallory. And if you can toss me share screen as well.
Absolutely. There you go. I can see your screen.
Awesome. So, thanks for the introductions. I think Omar and Mark set some good context for us. And what I wanted to talk about now and just introduce you to is the case study for PASI. Because Kuwait is an interesting place. Based in the Middle East, bordering Saudi Arabia and the Persian Gulf, it's one of the fastest growing countries in the world. And the Kuwait plan, the Kuwait Vision 2035, is focused on growth in their country, looking to invest by more than 11% increase in infrastructure and residential growth. So that's a really big challenge. And as you can imagine, that means a lot of new roads and a lot of new bridges and other things across the country. So this is a big challenge, but it's an even bigger challenge for PASI, the Public Authority for Civil Information, because PASI provides information and data to its citizens through apps like you see here for Kuwait Finder. So Kuwait Finder was developed to serve the users of the community and allowing them to get up-to-date, relevant information. This is really important because now there are more than 650,000 users within the system that are relying on Kuwait Finder every day. So it's really important that the underlying information is kept up to date and authoritative and relevant to help those citizens find their way. So with that, I want to throw it over and introduce Maher of PASI to tell us about what they did. Maher?
How to enhance our productivity as a government agency by applying machine learning for data automation. The Public Authority for Civil Information, PASI, has established the GIS program back in 2011. PASI is responsible to record all data about people, addresses, and businesses. All these data are stored and recorded in mainframe. But at the same time, all this data was linked together using GIS with more than 99.7% of links. PASI has developed a comprehensive base map for all the state of Kuwait. This base map was shared and used by more than 170 a GIS-based mobile application for the citizens and residents of Kuwait, which name is Kuwait Finder. Currently, we have more than 750,000 used downloads for Kuwait Finder, with more than 120,000 unique users who is using this application weekly. State of Kuwait is executing huge infrastructure projects all over the country. Following these changes, with the GIS forces available in FASI is a huge effort. Coping with these rapid changes requires continuous efforts to keep our data updated and at the same time available as an updated data source for all these agencies who is relying on us. FASI has decided to explore the use of machine learning tools in order to automate partially or full of our data set, especially building footprints and streets. Machine learning is something new for us. It is not something that we have already used before. So in order to be able to do this, we decided to do a rapid data assessment for the available data that we have in FASI. In order to be realistic, we checked our data from street center lines, building footprints, satellite imagery, and GPS data logs. In FASI, we have access to various satellite imagery. I am putting here some examples from Esri Arcgis Online, Airbus 2019, and Airbus 2018, and we have others. As you know, the problem that we are facing from using satellite imagery is that they have different properties, different capturing angles, and they have different orientations, and at the same time, different quality. As we mentioned, anonymized GPS logs that are coming from Kuwait Finder can be used also as an indicator for us to prioritize our working efforts on areas that we have changes or GPS points which are not snapped. As you can see here, the yellow streets are our digitized center lines, while the log GPS from Kuwait Finder is showing in different place. And this is how we were prioritizing our working efforts by clustering these non-snap GPS points to orient our resources. In a summary, imagery, it is not color balanced, it has the different capturing angles, different resolutions, not edge match, missing details, and poor color contrast. While our ground truth data, it has a missing data, it was incomplete, inconsistent, not uniform, it is centerline, not polygons, that can represent the street, the width of the streets, and also data shifts because of the capturing of the images. Based on this, in order to be able to start applying machine learning for our GIS tasks, we decided to start the creation of ground truth data for our targets, buildings, streets, and even parking lots. And at the same time, we initiated the creation of a baseline to measure our performance. So we measured our manual data entry operations, how much time they are taking to create the buildings, streets, and parkings, and the number of features, so that we are setting our baseline to measure our performance. This is an example of an area that it has around 21,000 building, streets, and parking features. It took around 13 days of working to do this As I mentioned earlier, machine learning is something new for us. So it is a learning journey. So we started testing the models and try to grasp and understand the different terms and keywords is used in this new domain. We spent around 3 months trying, testing, and at the same time selecting the best model that can fit our needs. We use Masker CNN, UNet, RoundNet, and even we developed our own model, which we call it RoadNet. At the end, we applied and used PyTorch UNet 152 architecture as our model and chose the best results. After the training, we start doing the prediction or the inferencing. This is a sample area that we run our inferencing on it. As I mentioned earlier, we use Airbus 2018 as our baseline. But while we are doing the prediction, we use our Airbus 2019 image in order to be sure how good our model is able to be to generalize. This area is around 600 square kilometers. Running the prediction using a normal Windows machine, F4 with GPU for sure, it took around 22 minutes to create the classified raster to cover this area. The raster itself is not enough. We need to convert it to our vector data that we need to use it. We have built a geoprocessing model that utilize the available tools in ArcGIS Pro for raster cleaning, building or majority filter, buffering, regularizing, eliminating elements, all these for the same area that we are talking about. It took 68 minutes to process the data that we have from the raster. And this is the output that we are doing. The 600 square kilometers, we had around 111,000 buildings, more than 78 state segments. The model took around 1.5 hours of processing, and for sure, we do not rely on the automation totally. We apply quality control to check the data visually, which is very important. It took around 2 days and 2 hours. The same data, if we apply our measuring control, it is around 119 days to prepare this data. And I think you can feel the difference. Quality control. Usually when we are applying machine learning, we are always relying on the matrices that are used by the model while training. But in GIS, we feel that it's something else. Because the model matrix does not mean if it is showing that it is highly accurate, does not mean that the output is correct or good for GIS. So we applied visual quality check for the data that we have. And we tried to classify the output of this data in order to figure out where are the problematic areas or what needs to be corrected or enhanced. The same area that you see now here, it is a visual quality check for 185 square kilometers, and you can see that the correct percentage for the buildings that are predicted correctly, it is 97%. Going deeper, we compared also visually how data is prepared by the users, our GIS technicians, how they are drawing it, and at the same time how it is created by the machine, which is on the right. And you can feel the actually the machine is doing much, I cannot say much better than the user, but it is in a good or very good situation that you can rely on it. We cannot pretend that we are done. We are still working to enhance the models that we are using, the data that we are feeding to the model, and at the same time, the post-processing workflows that we are using to create the final products that we are trying to reach. We hope that this presentation can help others to start their journey too. And we are happy to share our experience or our tries with the GIS community. At the end, I need to thank my team who participated in this journey. Without their efforts and understanding, nothing can happen. Thank you very much.
That's great, Maher. Thank you so much for sharing that example with us, and it is a really great example. I wanted to just summarize a few of the things that we heard, because what you've done is not only make PASI itself more responsive, but you've improved the accuracy for your citizens. You've saved time and money for your organization, but you've also expanded the internal capacity of your own team. So, as I understand that, it's probably allowing you to take on the next big, interesting project. So we can't wait to hear what's next from you and your team. I think we all appreciate, that you delivered on the improvements in accuracy and really helped your organization grow. So with that, I'm going to say thank you again, and I'm going to turn it back over to Omar.
Thank you. Thanks, Linda. Okay, so isn't that really beautiful? I mean, the idea of breaking down 5 years of human effort to under 13 minutes, that's exactly what Betsy has done with Spatial. And of course, it was not easy, as Mary explained. It is a journey. And a journey that starts with intention and understanding that it's a very iterative process, right? It's not going to happen immediately. That's something to understand, right? They went into loops of generating good training data, trying out different models, optimizing parameters, labeling again, etc., etc. But he ended up with an amazing model or a group of models that generating 90% accuracy. I want to show you a quick example that is using code in that case. So you've seen how to do the end-to-end work in Pro as the first demo. With that demo, I'm going to skim through an Arcgis notebook. So what you're seeing here is Arcgis notebook on Enterprise, which is the Jupyter notebook experience that comes with 300 plus data science, deep learning, machine learning packages, pre-configured and installed already, plus the analyses of Arcgis. So in the notebook, you can find a pretty much drag and drop experience for adding spatial analysis, adding data easily. So it's very good for anyone who's starting Python with GIS, or a data scientist who are used to Jupyter notebooks anyway, right? So in this notebook, real quick, what we're doing is we want to do high resolution line cover mapping with training data, and we want to do this for a large area. And we've done that, and the accuracy was almost 94-95%. So real quick, we're going to share that notebook with you anyways. It's publicly available. But real quick, we're doing the exact same steps. So we have a label layer for a specific area, a small area, right? And this actually is classifying each pixel, as you can see, with almost 10 to 12 categories like water, land, grass, impervious surface, building, you name it, right? So we are connecting, we want first to explore the training data for deep learning, right? So we're using the Python API in our GIS notebooks first to connect our training data. So we're getting the Kent County full label line cover. We're connecting to this layer. We are connecting to the name imagery. In that case, we're using it as the base imagery for this work. So we have the label layer, we have the name imagery. And then we want to specify a folder in the raster store that will be used to store our training data. So that's what we're doing here. We're defining that folder. And then we're exporting the data. So for any task that is related to this value chain, exporting data, training models, we're going to use Arcgis to learn, right? So I invite you to go and look for documentation for Arcgis to learn. It has amazing kind of capabilities. we're doing here is we are exporting these chips, and we're defining some parameters like the input drafted layer, the label layer, the output location, the tile size. And after we do the export, we want to train the model. So we're going to use a unit classifier. So we are importing from Arcgis to learn a unit classifier. We're defining the path for the training data. That's the folder where it has the image strips. And these are the image strips, by the way, again, images and labels, right? So you can see the chips here, and their labels are in the second folder. And we can actually use prepared data. Prepared data does a couple of things, one of which is producing different mutations from your existing training data. So the more examples we have, the more diverse examples, the better. So that's one thing that prepared data is doing, data augmentation. We are visualizing our data to have a quick look for it. So these are the chips, as you can see. And then we're loading the unit. So model equals unit classifier. We're passing the training data here. One of the things that Arcgis Learn does is automatically finding the learning rate. So the learning rate is an important hyperparameter. Think of it as a knob that you need to optimize for your neural network. You can read a lot about it online, but the bottom line is the learning rate finder is a capability that helps you find the optimal learning rate for different layers. So it identifies that, and then you start training your model, right? So this is the line of code where we're training our model. You can see that in each epoch, in each cycle of training, the accuracy is increasing until we reach like 91.5%. And I believe with other epochs we have reached almost 95% accuracy. We're visualizing the results of the model, ground truth versus predictions. As you can see, they're pretty much matching each other. We're deploying the model for inferencing. So we are uploading the model as a package on Portal. So think of it as having a model gallery on Portal where you can have multiple models and choose to use these models. Once you have these models deployed on the Portal, you can consume these models from Pro by connecting to your enterprise portal, or you can use it in a notebook like what I'm going to do right now. So this is when I am using the model, I'm calling the model for inference, right? So I'm using classified pixels. If you recall, we have seen this GD tool in Pro. Now we're writing the code for it, and now we can see the output. This is a glimpse of the output, so that's the named imagery. And that's the kind of the output. You can see how high quality is it. It's classifying these layers perfectly. And this is something that you can start doing today. Now with that said, I want to give you a quick list of other use cases and then shift to question and answer. So there are other things that you can do with Arcgis deep learning. For example, we have done work with partial boundary extraction. You can see here that we're not just extracting the boundaries of buildings, but the boundaries of the whole parcel. You need to pass training data for the parcel boundaries, and if you pass an attribute like the type of the parcel, whether it's agriculture, commercial, or residential, you can have this as an output as well. Extracting features from oriented imagery. We've seen two examples from overhead imagery, but what about oriented imagery? We have worked on a lot of projects detecting road signs, reading the text on road signs, for example, detecting potholes, any kind of features or assets in the road. Like in that case, for example, we are detecting road sign, we're detecting the text on this road sign, we are inferring the geolocation, and we have a blog post. We have a lot of blog posts, by the way. If you go to medium.com/GeoAI, you're going to find a lot of blog posts summarizing this work. So this is the dashboard that you can see for the detections of these road signs. You can see that we have inferred the location. You can click on any of these to see the exact road sign, see the bounded box that's detecting it, right? We have done some work detecting other features from oriented imagery, like features on houses. So detecting blight, graffiti, overgrowth on boarded windows, and then bringing this to a beautiful dashboard like this so we can see the specifics of attributes of these houses. We have done that with 180,000 houses with one of our customers, bringing down the time from almost a year of manually going through this data to almost 2 hours. We have done 3D reconstruction from LiDAR. This is something you can do. We have a public notebook for this. And the idea here is if you have aerial LiDAR, you can automate the process of coming up with the 3D scenes. So if you think about it, this is a complicated problem. On one side, we are detecting the building footprint. On the other side, we're trying to predict the type of the roof. So if you pass a parameter or an attribute for each roof type, whether it's shed, tip, gables, and so on, you can train a model to do the two things. So we are exporting the training data for 18
Yes, I'll go ahead and start the final poll question, which is really just getting a pulse on. Given what you guys seen, we'd definitely love to know if you are interested in speaking with an Esri subject matter expert. If you are, please let us know. And as we work through that, we'll go ahead and get started for. Omar, did you want to go ahead and cover some use cases, or should we just jump into the questions at this moment?
I'm going to jump immediately to the questions. I have them right now, but before that, I want to share in like 10 seconds some resources that our audience can make use of.
Absolutely. Okay, I'm going to go ahead and shut down the poll, and you have control again.
Cool. So we're going to share these resources with you guys in the email follow-up, but generally speaking, you want to have a look at the Arcgis to Learn online documentation, right? You can go and see a lot of sample notebooks. I've shown one example of a notebook. We have tens of these notebooks online. If you go to developers.arcgis.com/python/sample notebooks, you're going to find a lot of these notebooks. There's the GeoAI blog, which is medium.com/GeoAI. You'll find a lot of use cases with detailed technical details of how we've done that work. And there are a lot of videos. If you go to YouTube and search for Arcgis deep learning. One thing I want to share with you is the GeoAI group on LinkedIn. This is an online community we're building for sharing resources, news, and virtual events, and having discussions about spatial meeting AI. So really encourage you to go to LinkedIn and join this group and share your thoughts, share your work, ask questions. We're trying to build this community. And with that said, I want to go to the questions. So I am going to start. I'm sharing my screen and going through some of these questions and passing to some of my colleagues. So we have a lot of questions. So I'm going to try to go through some of these real quick and provide some answers. So one of the questions was, best classification is always from best input data. In this case, is imagery, any high imagery and open source that can be used for classification. So generally speaking, you can use the Arcgis world imagery. It's available in the Living Atlas, and you can access it in Pro and in Server. That's one source of imagery that you can use. If you need higher resolution, you can always leverage commercial providers like Planet or Globe or others. Okay. There was another question. The deep learning model use pre-training model. That's a good question. So you can use a pre-trained model, or you can train a model from scratch. In the GP tool in Pro, one of the parameters is you can choose a pre-existing pre-trained model. So let's say you have a model for building footprints, right? You don't need really to start from scratch. You can start with that model and fine-tune it with your new data, right? So I think you have both options. Okay, let's see. Okay, that's a good question. So the question is about, do I have to manually digitize training data? Can I also use existing feature classes for my enterprise or database? Of course you can use existing feature classes. Actually, that's one of the main advantages of doing deep learning in Arcgis, because you can just point it to an existing feature class of building centroids or building footprints or road segments, you name it. And then it can produce the image shifts from these feature classes. So the answer is no. You don't need to manually digitize. If you have existing feature classes, you can just use those, right? Okay, is there a way to extract parking lot from the Bing Maps imagery? Actually, you can extract pretty much what you want from any kind of imagery, as long as a human you can see it and detect it under 1 or 2 seconds. And you can use it, obviously, in Arcgis, right? So this applies to any kind of imagery. Do you need to create training data if you have to use for large database? I'm not sure I understand the question, but generally
in here. Omar, perhaps I can throw those to Maher?
Yeah, please. So Linda, if you can see these questions quickly, you can read them at that point.
Yeah, there's the first one, Maher, which is, are you applying distributed raster functionality to processes and preparing the data?
Actually, yes. We are applying it in two locations. First of all, we try to use the Arcgis Pro in order to do the creation of the raster data or the training data. But then, in order to speed up, because we were trying to have everything abstract from the software, especially of the data preparation. So we built and used Python using Jupyter notebooks and, for example, Ray in order to do a distributed raster processing for the data in order to create the training data.
That's great. There's a follow-up one here as well. How do you measure the accuracy assessment of the data?
Actually, this is a very challenging point, and this is really something that is not written very well. You need to explore it. We started this by following what is written on the blogs and documentation. If the model while training is producing good matrices or good learning curves, means that your model is correct. But when we are applying this on the data, especially, look, maybe this applies to other areas other than GIS, but in GIS, good learning curve does not mean that the output of the model is good for us. At the end, okay, we rely on the model matrices to see how our model is performing. But in fact, we decided to use visual quality check. Random, but for the sake of assessing our model accuracy, especially on the beginning, like